So we're going to start by taking a look at reaction mechanisms. And we're going to preface this by saying that we're going to draw on our quick review of naming. So now we're going to really start to dig into using molecules. So it's important that we're able to go back and understand what molecules we're talking about based on their names. So this is a quick review. Remember, if you're looking at something, say for example, like 1-butyl chloride, and if you were to move this chlorine from the 1 position to the 2 position, that would become 2-butyl chloride or S-butyl chloride. And if you were to move a methyl group also onto that 2 position, then that would become a tert-butyl chloride or 2-chloro-2-methyl-propane. And then the last example that we're looking at is an isobutyl. So that's where the chlorine is at the 1 position, but the methyl group is now at the 2 position, and that's what we refer to as 1-chloro-2-methyl-propane. So we've reviewed this in class before: N-butyl, S-butyl, T-butyl, isobutyl. And if, again, you want some additional practice here, being able to look at some tutorials or some additional practice problems would be helpful. So hopefully you can check your work. You've been able to draw your structure corresponding to each of the respective names. And again, if this is something you're not comfortable with, it's a great opportunity to use your individual whiteboards and practice. The other thing that we're going to take a look at today is a quick review of chair configurations. And again, this goes back to the idea of the more we practice drawing the structures, the more comfortable we'll feel with being able to assign both axial and equatorial, but also really being able to start to see why certain functional groups on a molecule attribute certain types of reactivity. So let's take a moment of practice. If I'm taking a look at this molecule and I had to do a chair flip, right? That's what I would see here. So this is just the flip of the chair that you see up here. If I wanted to draw these in their flat form, so where I'm just using wedges and dashes, how would I do that? Well, I'd have to identify a couple of key components. The first component is this chlorine is up in the axial position, and the hydroxyl group is down, also in the axial position. Whereas here, because I did the chair flip, anything that's axial becomes equatorial. So my hydroxyl group is now in the equatorial or down position, and my chlorine is also in the equatorial or down position. So let's take a moment. Let's check our work. Again, make sure that as you numbered, you paid particular attention to where you placed your substituents. Okay, so we're going to look at alkenes and alkynes. We left off talking about the pKa value for alkanes and alkene hydrogens being so large that there's really no base that's strong enough to remove a hydrogen from these classes of compounds based on the types of bases that we've looked at so far. That's not to say there aren't bases out there that can do that, but for our pKa table, we don't really have anything that's strong enough to take off those hydrogens. So when we're thinking about functional groups, excuse me, those hydrogens are not going to be the most reactive. It's going to be the hydrogens that are attached to heteroatoms like water instead. So we can think of these hydrogens as relatively unreactive. It's unlikely that we're going to form a carbon with a lone pair and a negative charge. However, there are other types of reactivity that we can see. So let's take a moment and practice drawing our equilibrium reactions. So if I had phenol, that's C6H5OH, and I can find that here with a pKa of 10, and HF with a pKa of 3.2 are poured into the same beaker, what's going to happen? So you need to go through a process that we've described previously, where you identify which is your stronger of the two acids based on pKa. That means the other compound is then going to function as a base. Then you need to think about what will form your conjugate acid and your conjugate base, and then think about what's the direction of equilibrium. And again, you can check the light bulb sheet for the solution to this problem. This is just a quick review of concepts that we had on exam 1 to make sure that everyone's on the same page before we get started looking at new material. Now, when we think about types of reactions, one of the things that I want you to start to think about are patterns. How can you identify patterns in the way that molecules react? So for example, there are 5 reactions that are described here: hydrochlorination, hydration, bromination or halogenation, hydroboration, and hydrogenation. What can you tell me about each of these patterns? What do you notice? If you said they all begin with an alkene, that's a great observation. And if you note that many of them involve halogens, that's also a great observation. Let's take a look in a little bit more depth in terms of these reactions. When we consider energy in reactions, we're looking at the energy of our starting materials, we're looking at the energy of a transition state, and then we're looking at the energy of our products. And one of the ways that we can parse a reaction is the heat of the reaction. So that's the difference in energy between the starting materials and the products. And then the activation energy. That's the amount of energy, or the hill, that your starting materials would have to climb in order to transform through a transition state into the products. When we think about a transition state, it's important that we define this clearly. It's an unstable species that represents the maximum energy that's formed during the course of a reaction. It's the maximum of the curve on an energy diagram. When we talk about then our activation energy, we're talking about the difference in the energy between the reactants and the transition state. This is what determines the rate of the reaction. If I have a large activation energy, then very few molecular collisions are going to occur with sufficient energy to reach the transition state, and I can think of my reaction as being slow. If my activation energy is small, then I have many collisions that are sufficient to generate energy to reach the transition state, and my reaction is fast. When we're drawing an energy diagram, it's important that we think about the heat of the reaction. This again is the difference in energy between the reactants and products. And then it's important that we make the distinction between an exothermic reaction. This is a reaction in which the energy of the products is lower than the energy of the reactants, so I'm giving off heat or energy, versus endothermic. This is a reaction in which the energy of the products is higher than the energy of the reactants. So this is going to be a reaction in which heat is absorbed. Notice, depending upon the type of reaction, I could have more than one activation energy. I could potentially form an intermediate, and I might have more than one transition state. So what we see here is an example where my activation energy to form my first transition state then forms an intermediate, and then with subsequent energy, my intermediate then undergoes a second transition state to form my products. What do we mean by reaction intermediate? This is an energy minimum that occurs between 2 transition steps. So my intermediates are going to be highly reactive, and very rarely would I be able to isolate them. The other critical term that we need to define here is a rate determining step. This is the step in a reaction sequence that crosses the highest energy barrier. It's also what we think of as the slowest step in a multi-step reaction. So take a moment and look at each of the components of this graph. Can you label them? What are components that are familiar to you? What might be some components that need further review? The good news is these are terms that you've covered in both Chem 110 and Chem 111, but if there are terms that aren't sounding familiar, this is a great opportunity to go back and revisit this section in the text. Now, here's the real question. What does a reaction mechanism describe? When we're thinking about a reaction and we're drawing a reaction mechanism with arrows, what does that really tell us? Again, take a moment, pause if you need, and really consider this question. A reaction mechanism describes which bonds break and which bonds form. It also describes the order and relative rates of various bond breaking and bond forming steps. So if a reaction is going to take place in solution, it might also indicate the solvent. And if there's a catalyst that's present, it might indicate the role of the catalyst. And then sometimes a reaction mechanism can actually indicate the energy of the entire system. However, it is not a list of reagents or experimental conditions that bring about the chemical transformation. A reaction mechanism describes how a transformation takes place. So let's think about patterns. The first pattern in mechanisms that we're going to explore is adding a proton. So in this example, curved arrows are going to show the redistribution of valence electrons while we're forming new covalent bonds when I take a proton from acetic acid using the base ammonia. Notice I have this symbol now. This is going to indicate anytime we're looking at a reaction mechanism, and specifically when we're looking at reaction mechanisms and patterns. Here, ammonia is a base, and my acetic acid I know is my stronger acid. It's not a strong acid because it has a pK of 4.76, but it is stronger as an acid than ammonia. So my ammonia, the lone pair, is going to take the proton. Remember, it only takes the proton, the electrons stay behind, so I break the bond between oxygen and hydrogen, and the electrons from that bond relocate onto my oxygen, forming a negative charge. So this becomes my acetate, a conjugate base, and my ammonium, my conjugate acid. And the direction of equilibrium is going to slightly favor to the right. Let's take another look at the addition of a proton using a different example, but the same type of pattern. So in this case, I'm adding a proton across the pi bond, or across a double bond. So I'm going to treat this double bond as though it were a lone pair of electrons. It's going to take a proton from hydronium, break the bond between oxygen and hydrogen, where the electrons are going to again relocate onto the oxygen. Notice I can only put the hydrogen on one carbon. This means that I'm going to form a carbocation on my other carbon because I no longer have satisfied the octet rule. We're going to talk a little bit more about carbocations shortly. What about a different pattern? Let's look at a pattern where we take a proton away. So this is reversing the pattern of one that we looked at initially. This is where I take a proton. Notice I have my acetate takes a proton, and again it breaks a bond and relocates the electrons onto my ammonium. Here I've taken a proton away from ammonia and added it to acetic acid. And you might be thinking, well, that looks very similar to what we just did. It did. This is actually the reason why we have to pay particular attention to equilibrium, because these patterns can oscillate back and forth and really be highly sensitive to our reaction conditions and circumstances like temperature and pressure, variables that if we alter, we could actually drive or affect the state of our equilibrium. If we think about pattern 3, this is the reaction of an electrophile and a nucleophile to form a new covalent bond. Just as a reminder, an electrophile is an electron-poor species that can accept a pair of electrons to form a new covalent bond, or a Lewis acid, whereas a nucleophile is an electron-rich species that can donate a pair of electrons to form a new covalent bond, a Lewis base. So if I take a look at this pattern, here I see a carbocation because I have a carbon that is missing all 4 bonds to complete the octet rule, so it has a positive charge. You could check that by calculating the formal charge. And I have chloride, a negatively charged ion. So here, my carbocation is going to be an electrophile because it has a positive charge, and my chloride ion is going to be a nucleophile. And when they react together, the negative, or the lone pair on the chloride, is going to attack the carbocation, forming a new bond. Note this is a covalent bond where the electrons are shared between the chloride and the carbon. Pattern number 4 is a rearrangement of a bond. So this is where the electrons of a sigma bond, or a single bond, break the bond from one atom and form a new covalent bond with an adjacent atom. This is not uncommon to see when we're looking at carbocations, particularly as we start to think about energy instability. So in this case, I break the single bond between carbon and hydrogen, and I move that bond over from carbon 2 to carbon 3. Notice when I do so, I simply move my carbocation onto carbon 2. This represents a more stable carbocation because it's a more substituted carbon. Pattern 5 is where we break a bond to form a stable molecular ion. So this is where a carbocation can be formed when a chemical species breaks off from one molecule, taking the electrons from the formal single bond with it. And the chemical species then formed is called a leaving group. This bond breaks because doing so forms one or more stable ions or molecules. Here's an example of pattern 5. So in this case, my bromide breaks the bond between Br and C. It leaves, forming a bromide ion, which is a stable ion in solution. And I form a tertiary carbocation, a very stable carbocation because carbon is substituted. So if we go back and we think about the reactions that I first introduced at the beginning of lecture, we have the addition of hydrogen halides, we have the addition of water, and we have the addition of halogens. So let's think about how we can use our patterns to be able to draw a mechanism for each of these reactions. Take a moment, pause, take your time to draw out and try and make sense of both the reaction mechanism and the patterns that you can observe. Let's take an example. So this is a reaction that can actually be carried out with pure reagents or in a polar solvent such as acetic acid. I have ethylene and HCl. In this case, the ethylene is going to abstract or take the proton away from HCl. It's going to then form a carbocation. That carbocation is highly reactive, and the chloride or Cl- ion is going to directly attach. Notice when I'm thinking about this type of reaction, right, the formation of something like a carbocation is, right, entirely dependent upon stability. So some of these are going to be reactions that literally occur in such a quick time period that you would not actually be able to observe any formation of an intermediate. So note, this is really critical. The addition of HCl is regioselective, which is to say that a regioselective reaction is one in which one direction of bond formation or bond breaking occurs in preference to all other directions. What do I mean by that? So here's an example. Here's propene and HCl. Note, I only observe the formation of 2-chloropropane and not 1-chloropropane. Why is that? Well, if you think about it, the carbocation that is formed is going to be formed on the more substituted carbon prior to the addition of Cl-. So this is a far more stable carbocation than having the carbocation on a primary carbon. This is what we refer to as Markovnikov's rule. So in additions of HX, where X could be any halogen to a double bond, H adds to the carbon with the greater number of hydrogens already bound to it, or the least substituted carbon. Markovnikov's rule is a great example of regioselectivity. So here, I see a couple of examples. So if you look, I form only one of the two drawn products. I form 2-iodo-2-methylpropane, the major product, and I don't observe any of the 1-iodo-2-methylpropane. Why is that? Can you use Markovnikov's rule to provide evidence for why you would only see the major product drawn? Likewise, if I look at the example that's at the bottom of the page, this is the addition of water and H2SO4. So H2SO4 in this case acts like that proton that's being donated. Why is it that I only see 1-methylcyclohexanol and not 2-methylcyclohexanol? Why is that? And if you take a look at that third reaction, can you predict what the major product would be? Here's our opportunity to make sense of Markovnikov's rule with a little bit more practice. So there are 4 examples for you here. And again, you can check your light bulb sheet to be able to determine whether or not your predicted products are correct. I'll also include the mechanisms for those reactions as well. It's important for us to make some distinctions about carbocations and regioselectivity. So here, when we're looking specifically at these types of molecules, we're looking at how they behave. Notice here, because it has a positive charge, that means it's the absence of electrons. So these hydrogens are arranged in trigonal planar, right, just as the methyl groups are here. So note there's an even distribution of electrons, just like there's an even distribution of electrons here. So a carbocation is a carbon atom that has only 3 bonds to it, so 6 electrons in its valence shell, and it bears a positive charge. So the bond angles are going to be approximately 120 degrees. This means that carbon uses sp2 hybrid orbitals to form sigma bonds. The unhybridized 2p orbital is going to lie perpendicular to my sigma bond framework, and it's going to have no electrons. What does that mean? Well, that translates to the fact that carbocations are going to be electrophiles. They love electrons. They're also going to be Lewis acids. That means that they're going to accept or receive electrons. Now, why does that matter? Well, it matters because the type of the type of carbon determines how reactive a carbocation is. So a tertiary carbocation is more stable than a secondary carbocation, and it requires a lower activation energy to form. A secondary carbocation is in turn more stable than a primary carbocation, and it requires a lower activation energy for its formation. Methyl and primary carbocations are highly unstable, and we're not going to observe them. So if I take a look at the order of increasing carbocation stability, anytime it's possible to form a tertiary carbocation, I want to form that because it's going to be more stable. Whereas I'm not going to observe the formation of ethyl and methyl cations. So the chemical basis for the regioselectivity and Markovnikov's rule is going to lie in the relative stabilities of the carbocation intermediates. So the proton of H bonded to any type of halogen is going to add to the less substituted carbon of the double bond to create the more stable carbocation intermediate. So notice you can actually draw what that looks like, and you can indicate which cations are formed due to stability and which are not formed due to instability. So take a moment, make sure that you have clear in your mind the naming that's associated with carbocations. So methyl, primary, secondary, tertiary, and quaternary. And think about why a quaternary carbocation would violate the octet rule. You can check your work. Next time, we're going to take a look at anti-Markovnikov. And just so that you can see the face behind the name, this is the gentleman Markovnikov, who was a Russian chemist who was responsible for this understanding that we now have of why carbons that are substituted are better for carbocations than carbons that are less substituted. Thanks. Have a great day.